We now discuss the solution of a problem from the section Algebra, and the problem is related to the divisibility and which is coming from the subsection number theory of the section Algebra. This question has appeared in the CSIR National Eligibility Test held on 16th September 2022, and it is from the section C. The given question is, consider the function f of n is equal to n power 5 minus 2n cube plus n, where n is a positive integer. Which of the statements are true? Which of the statements are true? It is from the section C, so it can have more than one answer. We are given 4 options. Option 1. For every positive integer k, there exists a positive integer n such that f of n is divisible by 2 power k. Option 2. F of n is even for every integer n greater than or equal to 20. Option 3. For every integer n greater than or equal to 20, either f of n is odd or f of n is divisible by 4. Option 4. For every odd integer n greater than or equal to 21, f of n is divisible by 64. We are given a function f of n given by n to the power of 5 minus 2n cube plus n, where n is a positive integer, and which of the following 4 statements are true? We will now discuss the solution of the problem in detail. We have the function f of n is equal to n to the power of 5 minus 2n cube plus n, where n is positive integer. Let's take f of n and take n common. So that is equal to n into, in brackets, n to the power of 4 minus 2n square plus 1. We see n to the power of 4 minus 2n square plus 1 is n square minus 1 whole square. Therefore, f of n is equal to n into n square minus 1 whole square. Right. Now we will consider the statements that are given in the options one by one and discuss those options. So let us first of all consider the statement that is given in option 1. That is, for every positive integer k, there exists a positive integer n such that f of n is divisible by 2 power k. Now, for every positive integer k, we can always have a natural number n is equal to 2 power k. So, for every positive integer k, there exists certainly a positive integer n is equal to 2 power k, and for this n, f of n is equal to f of 2 power k is equal to 2 power k into 2 power k whole square, that is 2 power 2k minus 1 whole square. So obviously 2 power k divides f of n because 2 power k is a factor. So clearly 2 power k divides f of n. So thus the statement given in option 1 is true. We move to the next option, option 2. In this, the statement given is f of n is even for every integer n greater than or equal to 20. It is easy to see that f of n is equal to n into n square minus 1 whole square is even when n is even. How? N is even, whatever it is, even multiplied by the another number, natural number, that will be even. So if n is even, because n multiplied by n square minus 1 whole square is there, when n is even, f of n is even. Right. Further, n is odd, and let us take n greater than or equal to 3. Why n greater than or equal to 3? When n is odd, n is equal to 1 also you can take it now. But here, n square minus 1 will give you 1 square minus 1, that is equal to 0. So to avoid that one, we have put n greater than or equal to 3. N is odd, n greater than or equal to 3. So n is odd, n square is odd. Then n square minus 1 is even. When n square minus 1 is even, it's a square. Even multiplied by even is even. So that will imply f of n is equal to n, which is odd, multiplied by n square minus 1 whole square, even. So odd multiplied by even is even. So thus f of n is even when n is odd, f of n is even when n is even. So f of n is even for every integer n greater than or equal to 3. Therefore, for every integer n is greater than or equal to 20, f of n is even. No problem. So therefore, the statement given in option 2 is true. Agreed. We move to the option 3. So option 3, for every integer n greater than or equal to 20, either f of n is odd or f of n is divisible by 4. We have already seen in option 2 that f of n is even for every integer n greater than or equal to 20. We have already seen this one. So that means either f of n is odd is not true. This is not true. This is not true. So f of n is even for every integer n greater than or equal to 20. If n is equal to, what about this one? F of n is divisible by 4. For that, we take n greater is equal to 22, which is greater than or equal to 20. So we take n is equal to 22, which is greater than 20. Then for this 20, f of 22 will be 22 into 22 square minus 1 whole square. So now f of 22 is not divisible by 4. Why? Because 22 square minus 1 whole square is odd. How? 22 is even. So even square is even. Even minus 1 is odd. Odd square is odd into odd is odd. So therefore 22 into an odd number. 2 divides this one, but 4 doesn't divide because 22 square minus 1 whole square is odd. So that means when n greater than or equal to 20, f of n is divisible by 4 is also false. So that means thus for every integer n greater than or equal to 20, f of n is even. That means f of n is not odd, and f of n is not divisible by 4. Is not divisible by 4. And. So this statement is completely the negation of the statement that is given in option 3. So that means therefore the statement given in option 3 is not true. Agreed. We go to the last option. The statement that is given in option 4, for every odd integer n greater than or equal to 21, f of n is divisible by 64. Let n greater than or equal to 21 be any odd integer. Then, because it is odd, we take it as 2m plus 1, where m greater than or equal to 10. Why? Because n is greater than or equal to 21, 2m plus 1 is greater than or equal to 21 will imply m greater than or equal to 10. Agreed. Agreed. Now f of n is equal to, n is what? 2m plus 1. F of 2m plus 1 is equal to, wherever there is n, you write 2m plus 1. 2m plus 1 into, in brackets, 2m plus 1 whole square minus 1 whole square. That is equal to 2m plus 1 into this one, 4m square plus 4m plus 1 minus 1. Minus 1 plus 1 cancels. You will get in brackets 4m square plus 4m. Whole square. 4 is common. 4 is common. Take out. It will come out as 4 square. 4 square is 16 into 2m plus 1 into, in brackets we will have m square plus m whole square. Now, notice that m square plus m is even if m is even. So, if m is even, m square is even, plus m is even plus even is even. No problem. If m is odd, m square, odd into odd is odd, m square is odd, plus m odd, odd plus odd is even. So, whatever may be m, whatever may be the integer m square plus m is even. So, therefore, m square plus m is even means 2k, where k greater than or equal to 55. Why it is? M is greater than or equal to 10 because n greater than or equal to 21. So, m is greater than or equal to 10 means m square plus m will be greater than or equal to 10 square 100 plus m 110. 110. That 110 is 2k. Therefore, k is greater than or equal to 55. Whatever it is. Whatever it is. Now, f of n is equal to 16 into 2m plus 1 into m square plus m whole square, this one is equal to 16 into 2m plus 1, m square plus m is 2k whole square, that is equal to 4k square. That 4 into 16 is 64 into 2m plus 1 into k square. So, clearly 64 is a divisor, 64 is a factor. So, this means f of n is divisible by 64 for every odd integer, n greater than or equal to 21. So, we have proved the statement that is given in option 4. Thus, the statement given in option 4 is true. So, summarizing all these things, in option 3, the statement given in option 3, we have shown that it is not true. Whereas the remaining ones, option 1, 2 and 4, they are all true. So, therefore, the answer to this question is options 1, 2 and 4. That is the detailed discussion of the solution of the problem from the subsection number theory, which is related to the divisibility. I am sure that you have understood the solution of this problem, and I wish you all the best. Thank you.